Welcome to The Explainer. All right, today we are going to demystify machine learning. We're going to break down what it really is, how it works under the hood, and get into the core concepts and workflows that are, powering pretty much everything, from your spam filter all the way to the most advanced AI out there.
So let's just start with a super practical example, something you deal with every single day: spam filtering. Now, the old way of doing this was totally rule-based. A programmer would literally sit down and write a rule. Something like, hey, if an email has the words free money, it's spam. Simple, right? But of course, spammers get clever. They change their tactics. The machine learning way of doing this is, well, it's a whole different ballgame. It doesn't depend on these rigid fixed rules. Instead, it actually learns the patterns of what spam looks like from seeing thousands and thousands of examples. And that's the magic. It can adapt and catch brand new tricks all by itself.
Okay, so here's the game plan for this explainer. First, we'll nail down what machine learning actually is. Then, we'll look at the 4 essential ingredients you absolutely need to make it work. After that, we'll cover the 3 main flavors of ML, dive a little deeper into the most common one, and finally, we'll tie it all together by looking at how a real project workflow, actually happens. All right, first up, what is machine learning, really, like at its absolute core? To wrap our heads around it, there's a really simple but super powerful framework we can use. Now, the official definition might sound a little academic, but stick with me because it's actually super useful. A system is said to learn if its performance at some task gets better with experience. See? PTE. This is the key. It means we're not coding in every single instruction. No. Instead, the system learns by finding patterns all by itself, straight from the data we feed it. And this TPE framework makes it all concrete. Let's go back to our spam filter. The task? Super clear. Classify an email as spam or not spam. The performance? Well, we can measure that. It's just the percentage of emails it gets right. In the experience? This is the most important part. That's the giant database of emails that real people have already marked as spam or not spam. The more of these examples it sees, the smarter it gets and the better it performs. It's that simple. Okay, so if machine learning is like a recipe, then what are the ingredients? It turns out, for pretty much any ML project, you're going to need 4 essential things. Think of these as the 4 pillars. First, and most obviously, you need data. Then from that data, you have to pull out what we call features. Features are just the specific characteristics the model is going to look at, kind of like clues. For a lot of ML, you also need labels. Labels are simply the correct answers, the ground truth for your data. And finally, you need an algorithm. That's just a set of rules or the procedure that does the actual learning, the thing that finds the connection between the features and the labels. And I cannot stress this enough. While you need all 4 of those things, data is absolutely king. The quality of your data will almost always matter more than which fancy algorithm you pick. You've heard the saying, garbage in, garbage out, right? Well, it's never been more true than in machine learning. Seriously, without good, clean data, the most powerful algorithm in the world is completely useless. All right, so we've got our ingredients. Now we can start looking at the 3 main recipes, or let's call them the fundamental approaches to machine learning. And what makes them different is really about the kind of data they use and what they're trying to accomplish. First up, and by far the most common, is supervised learning. The experience for this one is labeled data. What does that mean? It means for every piece of input, which we'll call X, we also have the correct answer, which we'll call Y. The goal is pretty straightforward. Learn the mapping from X to Y so well that you can predict the right Y for any new X you've never seen before. The best way to think about it? It's like studying for a test with a complete answer key. Okay, next we have unsupervised learning. Now, the experience here is the exact opposite. It's unlabeled data. We just have a bunch of inputs X, but there's no answer key. So the goal is totally different. This is all about exploration, about discovery. The algorithm's job is to just dive into all that messy data and find hidden patterns or structures or natural groups all by itself. And last but not least, we have reinforcement learning. And this one's a whole different beast. The experience isn't a data set you just hand over. It's an active agent that learns by doing. It tries stuff out in an environment and gets feedback, either a reward or a penalty. The whole goal is to figure out the best strategy, we call it a policy, to maximize its total reward over the long run. It's exactly like training a dog with treats for good behavior. All right, since supervised learning is the one you'll see most often, let's zoom in on that for a second. Inside this big category, there are really 2 main jobs a model can learn to do.
And the key difference is super simple. Classification is all about sorting things into buckets, into distinct categories. Is this email spam or not spam? Is this picture a cat or a dog? The model basically learns to draw a line, a decision boundary, to separate the different groups. Regression, on the other hand, is about predicting a specific number. What's the temperature going to be tomorrow? What's the price of this house? The model's job here is to fit a line or a curve to the data to make its prediction.
Okay, let's quickly jump back to the other two types just to make sure we're crystal clear on what their main goals are. So for unsupervised learning, remember, the whole point is to find hidden structures. The most common way to do this is called clustering, where the algorithm just automatically groups similar things together. A perfect real-world example is customer segmentation. A company can take all its customer data, throw it at a clustering algorithm, and discover natural groups of customers based on how they shop, all without having any predefined labels for those customers.
And for reinforcement learning, it really is all about learning from consequences. An agent tries something, gets feedback, that reward signal, and learns from it. This is famously how AIs learn to master incredibly complex games like chess and Go. But it's not just for games. It's also used to teach robots how to walk, or even to optimize a city's traffic light system to make traffic flow better.
Okay, so we've got the concepts, we've got the ingredients, we've got the main recipes. So how do people in the real world actually, do this? How do they build a working model? The important thing to know is that it's not a straight line. It's a cycle.
The whole machine learning workflow is fundamentally iterative, meaning you do it over and over. You always start with gathering and, very importantly, cleaning the data. Then you pick an algorithm and train your model. But you're not done. Next, you have to really analyze how well it's doing. Where is it getting things wrong? And this is the key part. You iterate. You go back to the beginning. Maybe you need to clean the data in a new way, or change the features, or even try a totally different model. And you just keep repeating that loop until you're happy with the results.
And listen, the whole point of this, the ultimate goal, it's not to build a model that's just really good at the data it's already seen during training. That's like memorizing the answers for a test. The real test is what we call generalization. Can your model make accurate predictions on brand new data it has never, ever seen before? That's what separates a good model from a useless one.
And that leaves us with a really important final thought. Because these incredibly powerful models learn only from the data we give them, they basically become a mirror, a reflection of that data. So it forces us to ask a pretty serious question. What patterns, what biases, what version of our world are we actually teaching them?